Why, hello everybody. Today we're going to start Chapter 3, in particular Section 13.1, so let's get started. The name of Section 13.1 is Three-Dimensional Coordinate Systems. All right, now what does that mean, three-dimensional coordinate systems? In the past, when you did your Algebra Trig 1, Algebra Trig 2, even Calc 1 and Calc 2, we dealt with a two-dimensional world, right? You had your x-axis, and you had your y-axis, and you plotted points like 2, 3, and all that type of stuff, right? Well, now we're going into the world of three dimensions. So we're not going to just have an x-axis and a y-axis. What we're going to have is an x-axis, a y-axis, and a z-axis. All right, and the way you can think of this is how we usually draw our x, y, and z-axis. But the way I want you to think of it is, think of it, you're back in Calc 1 or Calc 2, and you have an x-axis here, a y-axis here, and you actually take a z-axis that's coming up out of the paper. So the x-axis, y-axis makes you the floor, and the z-axis is going to be it'll be positive if you're above the floor, and it'll be negative if you're below the floor. Now we traditionally draw this like this, with the x-axis coming out, the y-axis, and then the z-axis. So in particular, let me show you how you would plot a point. If you wanted to plot a point with coordinates, let's say A, B, C, what you do is you're going to move in the x direction A units, then you'll move in the y direction B units. So right here is the point A, B, 0. You with me? Because I've gone in the x direction A units, then I've gone parallel to the y-axis B units, and if B is negative, you'd be going backwards. You with me? And then the z-coordinate is C, so if C is positive, you would go up above the xy plane, C units. And that's how you would plot your point, A, B, C. Okay? All right. Now, what if I want to figure out what surface in R3, and what is R3? R3 is the real number line times itself 3 times. So R3 is the set of ordered pairs that have x, y, and z, triple coordinates. What surface in R3 would be represented by the equation z equals 5? Well, now if you think about it, the x coordinates could be anything, but the z coordinate has to be 5. All right, now if you're struggling with that, let's go back to our Algebra 2 days. If I was wanting to draw y equals 2, just in two-dimensional space, in just 2 coordinates, you could say, well, gee, the y-coordinate's got to be 2, but the z-coordinate could be 2, but the x-coordinate could be anything. Do you remember doing that back in your Algebra Trig 1 days? So my x could be 1, and my y would be 2. My x could be 2, and my y would be 2. My x could be 3, and my y would be 2. And so we're looking at, back in R2, y equal 2 just being the horizontal line. That crossed the y-axis at 2. Now in 3 dimensions, we want z to be 5. So z has to be 5. But what does x and y have to be? X and y can be anything. So think about this. I could let x be 0, y be 0. So if I go in the x direction 0, y direction 0, z direction 5, I'd be right here. There's the point 0, 0, 5. Well, maybe I want to make x be 2, y be 0, z be 5. So I'd go in the x direction 2 units, that's to here, the y direction 0, so I'm not moving right, left at all, and then z5, I'm going to be going up 5 units. What if I wanted to make my x be 0, my y be 3, and my z be 5? Well, then I go in the x direction 0, so I stay here, y direction 3, and z is 5. I go up 5. 1, 2, 3, 4, 5. I'm right here. Well, what if I had like 0, 6, 5? In the x direction I go 0, in the y direction I go 6, so I'm going to go all the way over here, up 5. Well, you think all of these points have a height equal to 5 units above the xy plane. So do you see what you get? You're going to get a plane. Think about it. X and Y can be anything, but Z is 5. So if I went back and thought of having the x-axis here and the y-axis here, and Z is coming up out of the paper, I don't care where my coordinates could be 2, 3, 5. You'd go over 2, you'd go over 3, you'd go up 5 units above the origin. So if all the points are 5 units above the origin, we're looking at all the points that are 5 units above a plane that's 5 units above the xy axis. We doing okay? All right, what if we instead wanted to figure out what would be represented by the equation x equals 5? Well, now x has to be 5, but y can be anything. So where is x equals 5? X equals 5 is right around here. 1, 2, 3, 4, 5. Okay, that's x equals 5. Now, since y and z can be anything, we could go over 5 for x, and then we could let y be something, maybe 3, and z be 0. So you could go over this way, but z 0, so you're not going up. Or you could let x be 5, go over 5, and let y be 0, in which case I'm not going over at all, and then up 3. So if you think about it, with all of these, first x has to be 5, so you have to go over 5 for the x, but y could go over this amount, any amount, or z can go up this amount, or we could have y be something which you would go over up, and then z something. So what are we getting? We're getting this whole plane. This plane that's coming perpendicular to the x-axis, and it's intersecting it at 5. So you think what you're having here is x is 5, and since y can be anything and z can be anything, but x is stuck at 5, we have this plane that's perpendicular to the x-axis at x equals 5. Okay, let's look at another one. What if I have the equation x plus y equals 4? But before I do that in 3 space, let's go back and do it in 2 space. If you had to graph the line x plus y equals 4 in 2-dimensional space, where you just had your x-axis and your y-axis, does anybody know what that looks like? Well, it's a line for sure, right? It's a line. To graph a line in 2 space, what do you need? 2 points? How about if we look at the point when x is 4, y is 0, or when x is 0, y is 4? So I can go 1, 2, 3, 4 right here. 0, 4 is right here. And connecting the dots, this is what the line would look like. This being the x-axis, that being the y-axis. Now in 3 space, what's going on here? In 3 space, if I look at x plus y equals 4, notice they're not giving me any stipulation on what z is, are they? They're saying x plus y has to be 4, but z can be anything. Okay, z can be anything. But I have to satisfy the equation x plus y is equal to 4. So if you think about it, you have to, the x and y have to satisfy this equation. So your x and y coordinates are going to have to be somewhere on this line. But since z can be anything, you can go up any amount that you want. Well, if I have to be on this line, but then finally the z can be anything, I'm not only just get this line, but I'm going to get at any height. If I go up and go down, I get a plane that's perpendicular to the xy plane. You see what I'm talking about? So let's go back here and look at this. If I have x plus y equals 4, what I like to say is z is not in the equation. So I'm going to do the graph in the xy plane. The xy plane is the plane that's produced by the xy axis. So if you look at it, you've got this plane right here. Okay, there's my plane. Now since we have x plus y equals 4, as we noticed, if we let x be 4 and y be 0, it will satisfy it. And if we let x be 0 and y be 4, it will satisfy it. So let's see, 4, 0, 4, 0, 0 is here. 1, 2, 3, 4, right here. 0, 4, and we could just put zeros here for right now, would be here. 1, go over in the x direction 0, go in the y direction 4 units, 1, 2, 3, 4, and then we're going to go up nothing. So here's my line. And we can make little dotted lines to show it going back in the other sections. But now, since z could be anything, we could have made z be 3, in which case give me a height of 3 here. You could let z be 5, go up 5. You could let z be 8. And so since all these points work, think of lifting them perpendicular to the xy plane. And you see what we're getting here? We're getting this plane that comes perpendicular down to the xy plane and intersects that line. Okay, so this represents a plane. Now don't worry about it if you're struggling, because a lot of times students have never had 3 dimensions, and this is all new and you're struggling a little bit, but it will come as we go along. All right. We want to derive a quick formula, the distance formula in 3 dimensions. This is in your textbook in section 13.1. It says the distance P1, P2 between the points P1, which are x1, y1, z1, and P2, whose coordinates are x2, y2, z2, is given by the formula square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Now, do you remember the distance formula in 2-dimensional space? Do you remember doing that? Let's talk about that first. You notice 3D is very much like 2D. Okay, I see some of you are still copying that formula, so I'm going to wait while you're copying. All right, now before we derive this, I want to just go back to 2-dimensional space. Remember in 2-dimensional space, if you had 2 points and you had one, let's say, is x1, y1, and the other 2 was x2, y2, and you wanted to figure out the distance between those 2 points in 2-dimensional space. All right, notice if you dropped a perpendicular down here, this coordinate was x1. If you dropped a perpendicular down here, this is x2. If you dropped it over here, this is y1. Dropped it over here, this is y2. Now, I think most of you would agree that the distance from here to here, I'm going parallel to the x-axis, is the same as the distance from here to here. And what is the distance from point x1 to point x2 on the x-axis? Well, I think it would be parentheses x2 minus x1. And I think most of us would agree that the distance from here to here is the same as the distance from here to here. And the distance from y1 to y2 is y2 minus y1. And I'm going to call this little distance right here d, which is the distance between this point to this point. And I think most of you will remember the Pythagorean theorem says the hypotenuse squared is equal to the sums of the squares, is x2 minus x1 squared plus y2 minus y1 squared. And so if we take the square root of both sides, d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now that was your distance formula back when you only had 2 dimensions to worry about, the distance between 2 points in 2D, when you just had an x-axis and a y-axis. Notice the new formula just has a little z piece added to it. You see that? It's no different than the formula you had before, but it has a little z piece. If I were you, and I told you my Calculus 3 students are allowed to bring a cheat sheet, this is one thing you might want to put on the cheat sheet, okay, to help you. Before we go on, though, I don't want to just tell you people, let's just memorize. I want to show you where this formula comes from. So I have this picture that I just blew up. It's figure 9 in your textbook. Now notice, we want to find the distance between this point right here, P1, whose coordinates are x1, y1, z1, and this point right here, P2, whose coordinates are x2, y2, z2. We want to figure out this distance from here to here in red. All right, now notice, let's just do a few things here. Notice this point right here, if I come over here, all right, this point right here has coordinates x2, y1, z1. Okay, and this point right here, if we come over right here, has coordinates x2, y2, z1. So if you think to get to this point, all the points that had the same x coordinate like this are right along here. Okay, now, what I want to do first of all is I want to represent this distance from here to here. Do we all see that picture right there? I want to represent what this the distance from here to here is in the blue. Now notice, this point right here is x1, y1, z1. This point right here is x2, y2, z1. These 2 points have the same height. They're both a height 3 or a height 4 or height 5 above the xy plane. You see that? So I could draw my xy axis, you with me? With that height at z1, and I could say, the distance between these 2 points, I can just use my old formula in 2D since they have the same height. You with me? They're in that same plane. You with me? So to find this distance right here, I'm going to use my old distance formula right here. Square root of x2 minus x1 squared plus y2 minus y1 squared. And that's that distance right here. That distance right there is square root of x2 minus x1 squared plus y2 minus y1 squared, which I'm going to call little d. That's this little distance right here. But now, what's this length right here? From here to here. Now look, this point and this point, notice they have the exact same x-coordinate and y-coordinate. They're x2, y2, this one's z1, this is z2. So with this one, you know you went over x, you went over y, you went up z a certain amount. And this one, you're going up a different z. So if we have the same x-coordinate and y-coordinate, but different z's, this distance right here is just going to be z2 minus z1. And notice this is straight up perpendicular to this base, this little right angle here. So when I want to find this distance, what I have here is a right triangle. And this is my hypotenuse, because this is my right angle right here. So to find this length right here, which I'm going to call big D, all right, what I'm going to use here is big D squared is equal to the squares of the legs. But remember, little d was this. So if I square it, I just get what's inside. Plus, I had this z2 minus z1 squared. So if I want to find out what d is, the distance from this point to that point, all I have to do is take the square root of both sides. Now, do we have to derive this every single time? No. It's probably much easier if you just remember your distance formula looks just like the one you had back in your Calc 1, Calc 2, but you got this z piece because we have z coordinates. Okay? All right, so let's practice a little bit. First problem we want to do, very simple little problem, is determine the distance between the points 3, 2, 1 and 1, 3, 7. It's just like the distance formula you had back in Calc 1. So our distance formula is big D, our distance between 2 points, is the square root of x2 minus x1 squared plus y2 minus y1 squared. But now we have to add z2 minus z1 squared. So this is going to be my x1, y1, z1, and this is my x2, y2, z2. So my distance is going to be square root of 1 minus 3 squared plus, we have to subtract our y coordinates, so it's going to be 3 minus the quantity 3 minus 2 squared plus the quantity 7 minus 1 squared, which is going to give us the square root of, let's see, 1 minus 3 is negative 2, square it gives me 4. 3 minus 2 is 1, square it gives me 1. And 7 minus 1 is 6, square it gives me 36. Okay, I subtracted my x coordinates, my y coordinates, and my z coordinates. And 36 and 4 is 40 plus 1 is 41. So my distance is going to be square root of 41. Okay, not hard at all. But this is our first formula that you really want to memorize. It's going to make life a little bit easier if you do. Okay, let's go on. Now, before I look at this picture, what's a circle? In two-dimensional space, what's a circle? To get a circle, you need a center, right? You need a center, and you need a radius. And everything in the circle are all the points that are the exact same distance, the radius, from the center. that if you measure how far you are from the edge of the circle to the center, it's always whatever your radius is. So the radius might be 5 or 2 or 6, right? That's what a circle is. Well, a sphere is no different. A sphere is a set of points that are all equally distant from some center. Now, in this particular case, my sphere here has a center HKL. All right? And I want to look at all the points x, y, z, all the points x, y, z that are on that sphere. They are all r units from the center. So in other words, the distance from any point on the sphere x, y, z to the center HKL has to equal the radius. And we just did the distance formula, right? Well, what's the distance from the point x, y, z to the point HKL? Well, let's see. That would be the square root of x minus h squared plus y minus k squared plus z minus l squared. And we have to have that equal to r. Well, I don't really like equations that have a square root in them, so if I square both sides, I'd get x minus h squared plus y minus k squared plus z minus l squared would equal r squared if I square both sides. So this is the equation of a sphere. What particular sphere? The sphere whose center is HKL. That's the center. So notice this is where the center shows up, HKL, and whose radius is r. Notice it's r squared. Okay, so I have that typed here for you. An equation of a sphere with center HKL and radius r is given by x minus quantity x minus h squared plus y minus k squared plus z minus l squared equals r squared. And note, it's very similar to the equation of a circle that you did before, right? It's no different, but it has that z piece because we're now in 3 dimensions. And notice your center HKL show up there. All right, so let's just play with this. What if I gave you the equation x minus 4 squared plus y minus 7 squared plus z minus 8 squared equals 25. That's in that form, right? What's the center of that circle? Well, notice here's your h, k, and l. So my center is going to be my h is 4, my k is 7, my l is 8. So this particular circle has its center equal to 4, 7, 8. And notice r squared is 25, so r would be 5. So this circle would be the circle whose center is 4, 7, 8, and then you go to 5 to the right, 5 to the left, 5 up, 5 back, all the points that are 5 units away from that particular center. Okay, let's try one more. What if I gave you this? What if I gave you x plus 5 squared plus y squared plus z minus 2 squared equals 7. Okay, what if I have that for my equation for my sphere? What would the center of that sphere be? My center would be, well, it's x minus h, but I have x plus 5. So what would the x coordinate be of the center? Negative 5. What would the y coordinate be? 0, because y squared is the same as y minus 0 squared, so it would be 0. My z would be 2. Now notice r squared is 7, so my radius is root 7. So this particular circle would have center negative 5, 0, 2, and would have a center root 7. Everybody realize that y squared is the same as y minus 0 squared, right? So that's how we got that to be. Now notice, what if I take my sphere here, and I say, well, you know, what if I want a very special sphere whose center is the origin, 0, 0, 0, and I want my radius to be r. Well, if the center is 0, 0, 0, 0 goes in for h, 0 goes in for k, 0 goes in for l. So we're going to get x minus 0 squared plus y minus 0 squared plus z minus 0 squared equals r squared. Or you could write it much succinctly as x squared plus y squared plus z squared is equal to r squared. And that would be the equation of a circle whose center is 0, 0, 0, and whose radius is r. So we're going to see that a lot. and we'll just put that here in particular. In particular, if the center of the circle is the origin, then the equation of the sphere is just x squared plus y squared plus z squared equals r squared, which is a handy thing to know. Okay? All right, now what if I have this? They give me the equation right here, x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 is equal to 0. They want me to show that it's an equation of a sphere, and in the end, I want to determine its center and its radius. Okay, now first of all, before I do anything, I'm just going to copy. I'm going to go back to my notes and say, what's the general equation for a sphere? It's x minus h squared plus y minus k squared plus z minus l squared equals r squared. So I'm going to write that down. My general equation for a sphere is x minus h squared plus y minus k squared plus z minus l squared equals r squared. Now the equation we have to deal with is x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0. Okay, I just recopied the equation. Okay, I'm just going to move this up to give myself a little bit of space. Now I want to put this equation in this form. Do you remember doing completing the square? You've done that before, right? We're going to complete the square. Do you remember how you complete the square? First I'm going to put the x pieces together. X squared plus 4x. I'm going to put the y pieces together. Y squared minus 6y. I'm going to put the z together. Z squared plus 2z. And then I'm going to put negative 6 over there by itself. So I subtracted 6 on both sides. Now, do you remember? I want this to look like that. Do you remember what you do when you complete the square? What do you do? Let's look at a perfect square. This is a perfect square. X plus 2 squared is a perfect square. X plus 3 is a perfect square. X minus 5 is a perfect square, right? Notice if I multiply these out, I'm just multiplying these out in my head. Notice with all of them, if you take this coefficient and divide it by 2, you get 2, and square it, you get 4. You find out what that number needs to be. If I take 6 and divide it by 2, I get 3. Square 3, I get 9. Take this negative 10, divide it by 2, I get 5. 5 squared is 25. You can see why that's true, because if you multiply x plus a squared out, you'd get x squared plus 2ax plus a squared. So notice if you take this coefficient, 2a, and divide it by 2, you get a, and square it, you get a squared. Okay, so we just have to divide by 2 and then square if we have this coefficient and we want to figure out what I need to have here. So going back here, I want this to be a perfect square. So I have x squared plus 4x plus what? What do I need here for that to be a perfect square? If we take 4 and divide it by 2 gives you 2, and square it gives you 4. So I'm going to add a 4 on this side and a 4 on that side. I want this to be a perfect square. Well, if I take 6 and divide it by 2 gives me negative 3, and negative 3 squared is 9. I need a 9 here. But whatever I do to one side, I better do at the other side to make them equal. And I want this to be a perfect square. If I take 2 and divide it by 2, I get 1. Square it, I get 1. So I better add a 1 on that side. Okay? And so therefore, now if we factor, what's x squared plus 4x plus 4? If you factor it, you'll see that's x plus 2, quantity squared. Can I factor this? Y squared minus 6y plus 9. Can we factor that? Let's try factoring y squared plus 6y. I think if you divide 6 by 2, you can see it's going to be y minus 3, isn't it? Because that gives you y squared minus 3y minus 3y is minus 6y. Negative 3 times negative 3 is 9. So it's going to be y minus 3 squared. And this one, we want to factor this one right here. Let's see what we need. We need z, divide 2 by 1, you get plus 1. So it's z plus 1 times z plus 1, or z plus 1 squared equals, let's see, 1 and 9 is 10, and 4 is 14, minus 6 is, 15. 15 minus 6 is, I guess, 7, huh? No, 15 minus 6,
14.
4 and 1 is 5. 14 minus 6 gives us 8, if I subtract it right. Okay, thank you. So, what is our center? What is our center of this circle? Our center is, since it's plus 2, it's a negative 2 for the x-coordinate, it's a plus 3 for the y-coordinate, and z is going to be a negative 1. And since r squared is 8, r is root 8, which we can write as square root of 4 times square root of 2. So I think 2 root 2 would be the better way to write the radius. Okay? So when you have an equation that gets all jumbled up like this one, you can do something that we call completing the square to figure out, to put it in the form. It's in the form of x minus h squared plus y minus k squared plus z minus l squared equals r squared. It is the equation of a sphere. Okay, let's move on. And this little picture here is quite nice. Let's just look at it. Notice they're just showing, if you wanted to plot the point A, B, C, you go over in the x direction A units, in the y direction B units, up in the z direction C units. Now notice this point, I just want to look at this picture for a little bit before we go on and do a few more problems. What if I'm looking at this point ABC, and I want to know how far is it from the xy plane? Now where is the xy plane? This is the xy plane. You see that? That's the xy plane. Okay, there's, oh, excuse me, xy plane. This is the xy plane. Everybody's nodding their heads. No, don't nod your heads. Xy plane is xy. This is the xy plane. And I want to know how far is this point from the xy plane. Can you see? You see what we did is we dropped a perpendicular from ABC to the xz plane, from ABC to the yz plane, from ABC down to the xy plane. Now notice when we plot this point, you go over A, over B, up C. How long is this line segment right here? C, isn't it? Do you all see that? Because to plot this point, ABC, you go in the x direction, A units, then you go parallel to the y-axis, B units, and then you go up, C units. So the length, this right here, is C units. So how far is this point ABC to the xy plane? C units. Notice the xy plane, the z coordinate is C, and you're C units away from the xy plane. What if I want to know how far am I from the xz plane, which was what I was pointing to a few minutes ago? Where's the xz plane? Here is the xz plane, xz. Now if I want to know how far this point is to the xz plane, I'm going to drop a perpendicular over to that xz plane. And I want to know how long is this unit? Do you all agree that this length and this length are the same? How long is this one? B, right? Because we went over A, over B, up C. From here to here is B. So the distance from the xz plane is B units. Notice, if you look at xz, who's the odd man out? Y. What's the y coordinate? B. So what do you think if you wanted to figure out your distance from the point ABC from the yz plane? If you had to guess, it would be the what coordinate? The x coordinate, A units. And let's see if that works. Here's the point ABC. If we want to go to the yz plane, notice here's the y-axis, here's the z-axis. So this is your yz plane right here. So the point in the yz plane would be 0 BC. And if you notice, we want this length right here, which is the same as this length right here, which is the same as this length right here. And how long is that? A. It's A, because it's the odd, it's the coordinate that's not in yz, x coordinate. Okay, so let's look here. Let's just look at another problem. Look here what I have right here. I have the point right here, -4, 3, -5. Now notice the x coordinate is negative. So instead of going positive x-axis, we had to shoot back negative x-axis. Do you see that? They had to go in the opposite direction of the x-axis. Now the y-coordinate's 3, so we go positive direction of the y-coordinate 3 units. But then since z is a -5, what do? We go down 5. Not up 5, because it's down below the xy plane. And that's where the point -4, -3, -5 would be. What would the distance, what if I wanted to do this quite quickly, and I'm looking at this point right here, and I want to figure out what is its distance. What's the distance, -4, 3, 5, to, let's do the XY plane. Using the trick that we did a few minutes ago, what coordinate would it be? It would be the Z coordinate, wouldn't it? It would be 5 units. It would be 5 units. And as you can see why that's true, here's your XY plane right here. Here's your XY plane. If you take a perpendicular up to that plane, you're talking 5 units. What if I wanted to get the distance of that point to the YZ plane? What coordinate would I be looking at? YZ, I'd be looking at the X coordinate, so it would be 4 units. And if you think about it, where we are right here, if you want to look at YZ, YZ is right here. YZ, YZ, this thing is back 4 units. It's the same distance as this right here. Okay, moving right along. We're going to now go through a few examples, a few problems. I like to pick out the even problems. We'll go over the problems you're going to do in your homework are going to be the odds that are like sister problems to these. So let's just go over a few of these. They want to talk about the projection of the point 235 onto the XY, the YZ, and the XZ planes. All right? And then they want me to draw a rectangular box with the origin and 235 as opposite vertices, and with its faces parallel to the coordinate planes. Label all vertices of the box. Find the length of the diagonal of the box. Okay, let me just slide this little sheet under here. I can move this more over to the center for you to see what's going on here. Now, I might not do all of it, but let's start doing most of it. If I wanted to plot the point 235, okay, that's the first thing I got to do. I got to go in the X direction 2 units. Okay, we're talking about the point 2, 3, 5. Then we're going to go in the Y direction 3 units. 1, 2, 3. This length right here is that much. See, I want to measure it. In fact, I'll just take a sheet of paper and help measure it. If this is 3 units, from here to here is 3 units, I want to go 3 units in the Y direction. Right there. Now notice, this point right here, if X is 2, this is the point 2, 0, 0. Because we went in the X direction 2, Y direction, Z direction, nothing. Then we went in the Y direction 3 units. So this point right here is 2, 3, 0, because we're not doing anything in the Y direction. Now we got to go up 5. Well, let's see. 1, 2, 3, 4, 5. That's 5 units for the Z. So let's say this is about 5. So I want to go 5 units up in the Z direction. And here's the point 2, 3, 5. Notice we went in the X direction first, then we went in the Y direction, and then we went up in the Z direction. And that's the point 2, 3, 5. Okay, now notice, here's 0, 0, 5. So I'm going to draw a parallel to this from up here. Because see, our box has a height of 5, so we're up 5. If I draw a parallel this length in this direction, it's going to look about like this. Should have brought a ruler. Okay. If you put this parallel to it and draw a parallel to this back here, and then bring this down, 1, 2, 3. There's a little box that might help us thinking when we're plotting this point 235, we go in the X direction 2, in the Y direction 3, and then up 5 units to get to this point. Okay, now they want me to do a few projections. They want to know what are the projections of the point 235 on the XY plane. Well, that's the point right here, because you see you're taking the perpendicular down from that point down to the XY plane. Now if you think, if you're in the XY plane, what's your Z coordinate? 0. But we're going straight down, and so the X and the Y stay the same. So the projection onto the XY plane is going to be the point 2, 3, 0. Because if you're on the XY plane, you have no height. Your Z is going to be 0. Now let's do this one. Let's get the projection onto the YZ plane. Now before we do anything, let me ask you, if you're in the YZ plane, here's the YZ plane. You're back here in the YZ plane. What's your X coordinate? If you're on the YZ plane, your X coordinate has to be 0, because if your X coordinate is anything else, you're going to be going away from that YZ plane. Do you see that? So if you're in the YZ plane, your X coordinate has to be 0. So if the x-coordinate is 0, these two will stay as they are. And if you notice, where is 0, 3, 5? Well, if I go over 0, stay there, go over 3, up 5. Here's the point, 0, 3, 5. That point's in the YZ plane. You see, it's back there in that octant right there. Now let's try the XZ plane. If I want to take the projection of the point 2, 3, 5, 2, 3, 5 to the XZ plane, if you're in the XZ plane, what coordinate is equal to 0? Y. So if y is 0, then the x-coordinate has to be 2, the y-coordinate has to be 3. Where's 2, 0, 5 going to be? Go over in the x direction 2, go in the y direction 0, stay where you are, then go in the z direction 5. Right here is the point 2, 0, 5. And notice that's just dropping a perpendicular from that point over to the XZ plane. But the quick and dirty way to do it, if you're doing a projection of a point onto a plane, if I want to know the projection onto the xy, I say, oh, z 0, and then the x and y stay as they were. If I want to get the projection onto the yz, oh, x is 0, let the other two be as they are. Okay? They also want me to drew my rectangular box as opposite vertices with its faces parallel. We did all that. Label all vertices of the box. Well, I've got this one, this one, this one. I didn't label this one or this one. So let's do this one right here. That one you're going over x 0, then you're going over y 3, and up nothing. So that's going to be 0, 3, 0. What would be the coordinates of that point right there? Well, how much in the x direction do I go? 0. How much in the y direction do I go? 0, and then I just go up 5. So that point right there is 0, 0, 5. Okay, let's look at another problem. Next one I want to look at. Find the distance from 3, 7, negative 5 to each of the following. 3, 7, negative 5 to each of the following. The XY plane. Now remember the quick and dirty, the way we did it? Let's talk. If I plot this point, 3, 7, 5, I go over x3, then I go over y, 7, so I'm right here someplace, right? So that's 3, 7, 0. And then what do I have to do? I have to go down 5 units. Now do you see, this is your xy plane, but you're going down 5 units. So the distance this point is to that plane is 5. The quick and dirty way to do it, if they're talking about xy plane, just take the absolute value of the z-coordinate. Do you see that? The absolute value, xy, the absolute value of the z-coordinate is 5. So doing the quick and dirty, what if I wanted to find the distance from 3, 7, negative 5 to the yz plane? This is the yz plane. It would be what? The absolute value of the x-coordinate. And what's the absolute value of the x-coordinate? 3. Does that make sense? Well, let's just see. But after a while, you're going to want to do it the quick and dirty. If I go over 3, go in the x direction 3, in the y direction 7, so that point right there is 3, 7, 0, and then down 5. Down 5. And I want to know the distance to the yz plane. That's this distance right here, isn't it? Right? The perpendicular, because it's the same as this distance here to that. And this distance is the same as this distance, which is the same as this distance, which is the x-coordinate. Quick and dirty, if I want to find the distance from this point to the xz plane, it's going to be the absolute value of the y-coordinate, which is going to give me 7. Okay, now this one's not as easy. We didn't do one like this. We want to find the distance of 3, 7, negative 5 to the x-axis. So let's draw that little box like we did before and see if we can figure that out. We were looking at the point 3, 7, negative 5. So we went over in the x direction 3, then we went in the y direction 1, 2, 3, 4, 5, 6, 7, right here. So right here is 3, 7, but we've got to go down 5 units, to right here. This is 3, 7, 0, and here's 3, 7, negative 5. Now if I draw my little box, and we can actually have this come down like this and go across. Now we want to know the distance that this point is to the x-axis. So if I drew a perpendicular, here's my perpendicular. Now how am I going to get that? Well, let's see. When I plot this point here, I went over 3, right? Then I went in the y direction 7. Then I went down in the z direction 5. Now notice when I drop my perpendicular to the x-axis, I get this little right triangle here. Notice it's the right triangle that's formed by this point to the x-axis. Now when you're going perpendicular to the x-axis, you're going to keep your x-axis as 3, 0, 0. Right? Because I'm going perpendicular to the x-axis. So when I go perpendicular to the x-axis, the x-coordinate stays the same. If I'm on the x-axis, this point's going to have a y-coordinate of 0, 0. Now there's two ways I could do it. I could just say, oh, let's just use the Pythagorean theorem here and say d squared is 7 squared plus 5 squared, or d squared is 49 plus 25, which is 74. So my distance is root 74. That's one quick, because I drew my little parallel, I think they call it a parallel pipette, or you can think of it as a shoebox. But another way to do it is if I want to know my distance to the x-axis, if you drop that perpendicular, the x-coordinate is going to stay the same as 3, but if you're on the x-axis, those would be 0. You could also just use your distance formula. And your distance formula here would be square root of 3 minus 3 squared, plus 7 minus 0 squared, plus negative 5 minus 0 squared, which would be square root of 0 plus 49, plus 25, which is square root of 74, which we had before. Okay? Either way, you'll find right now you're going, oh, Ms. Strocko, I much prefer doing the Pythagorean theorem thing that you did. But the point is this, you might not want to be drawing that box every single time, and then it might not be as obvious. So the quick and dirty, if we're looking at 3, 7, negative 5, over 3, over 7, down negative 5. And I'm going to write this down as 3, 7, negative 5. If they want me to get the perpendicular distance to, okay, the y-axis, if I'm going to the y-axis, what coordinate's not changing? The y-coordinate. It will stay as 7. But since I'm on the y-axis, the x and the z's are going to be 0. And I'm going to use my distance formula. My distance is going to be square root of 3 minus 0 squared, plus 7 minus 7 squared, which is 0, plus negative 5 minus 0 squared. And it looks like we get the square root of 9 plus 25, which looks like square root of 34. Okay? If I wanted to find the distance of 3, 7, negative 5, 3, 7, negative 5, to the z-axis, if I'm dropping that perpendicular, okay, or I guess maybe it might make it look, I guess it looks perpendicular to that. What coordinate's not changing when you're going to the z-axis? The z. So x and y will be 0, but that will be negative 5. And you can do the distance formula from this point to this point, which would give you square root of 0 minus 3 squared, plus 0 minus 7 squared, plus negative 5 minus negative 5 squared is 0, which gives me square root of 9 plus 49, which is square root of 58. Okay? All right. Let's look at this one. Easy problem. Find an equation of the sphere with center 6, 5, negative 2 and radius radical 7. Piece of cake. You want the equation of a sphere whose center, HKL, is 6, 5, negative 2, and we want the radius to be square root of 7. We just did that a few minutes ago. Remember, our equation for a sphere was x minus h squared plus y minus k squared plus z minus l squared equals r squared. So what do you have to do? You fill in the blanks. That goes in for your center. So 6 goes in for h, 5 goes in for k, and minus 2 goes in for l, and r squared would be 7. And this is your equation. Okay, now think about what this sphere would look like. Where's the center of that sphere? The center of that sphere is the point 6, 5, negative 2. 6, 5, negative 2. All right. I want to draw it a little bit. We want to look at 6, 5, negative 2. All right. Go over 6. 1, 2, 3, 4, 5, 6. Go over 5. And then we're going down 2. How far is 6, 5, negative 2? Let's do distances. Distance 2, xy plane. How far is it from the xy plane from this point? How far is it from this point to the xy plane? 2. What's the distance to the yz plane? The yz plane would be 6. How about the xz plane? That would be, xz plane would be y, which is 5. Okay. All right, now, my point is this. This particular sphere has a radius of root 7. How big's root 7? Is it bigger than 2? Is it bigger than 3? No, it's not. Root 7 is going to be between 2 and 3, right? Maybe 2.5 something. There's no sense for me to turn this calculator on, but just to get an idea, if we wanted to take the square root, let me hit clear here first. Take the square root of 7, and I'm going to give me a decimal for it. It's not showing up on the screen, but I want the square root of 7. Let's do it again. If I want the square root of 7, and let's just put a decimal point in there. Square root of 7 point is 2.645, about 2.6. All right, so my radius is approximately 2.6. Now think about this. Here's the point. From here to here is 2 units, right? So my sphere is going to go a little bit higher than that. You with me? It's going to be a little bit higher. Now what's this distance from here to here? 6. And from here to here is what? What's this length right here? Oh, this is 6 because you went over 6, so this distance is 6. Then you went in the y direction 5, so this distance is 5, and then we went down 2. So my point is, if my radius is 2.6, I can go 2.6 to the left, 2.6 up, 2.6 down, 2.6 back. My sphere is going to look something like this. When I go 2.6 in this direction, am I going to hit the yz plane? No. Am I going to hit the xy plane? Am I going to hit the xz plane? No. Am I going to hit the xy plane? Now think about it. Use your intuition. What is the intersection of this sphere with the xy plane going to look like? If I have a sphere and I am bringing it up and you're cutting it off with a plane, what's that intersection going to look like? A circle, isn't it? You're going to have a circle here. Okay? Now we got the equation. We can picture this sphere somehow. Notice they say describe its intersection with each of the coordinate planes. Now let's suppose, Mrs. Strocko, well, let's not even suppose. I'm telling you, look at this sphere, and when this sphere comes up and intersects the xy plane, I'm saying I'm going to get like a circle. Now let me ask you something. If you are on the xy plane, what can you tell me about the z-coordinate of every single point that's on the xy plane? It's 0, isn't it? Because if you're on the xy plane, you go over x, over y, and how much up do you go? You don't go up anything, do you? You don't go down anything because you're still in the xy plane. So z is 0. So if I plug in z equals 0 into this equation, I'd get x minus 6 squared plus y minus 5 squared plus putting a 0 in for z. 0 plus 2 is 2. Square gives me 4 equals 7. Or I get, back in my old traditional circle days, x minus 6 squared plus y minus 5 squared equals 3. You get the old circle whose center is 6, 5, and whose radius is radical 3. You've got a circle. Okay, now a few minutes ago I was saying, looking at this sphere, is it ever going to intersect the xz plane? And I took the time to measure what this distance was and realized it was 5, and so if my radius was 2.6, I'd never get to the xz plane, right? But suppose you didn't think about that. You just decided to plug it in. Well, what if I want to take the intersection with this sphere with the xz plane? What can you tell me about every point in the xz plane? Every point in this plane. You go over x. How much y do you go over? 0, because if you go over y, something that takes you off the xz plane. So in the xz plane, y is 0. Well, if y is 0 and I plugged it back into this equation, look what I get. X minus 6 squared plus 0 minus 5 squared plus z plus 2 squared is 7. I get x minus 6 squared plus 25 plus z plus 2 squared is 7. Or I get x minus 6 squared plus z plus 2 squared is, what's 25 minus 7? 18? Negative 18. Can you have things that are squared added together to give you a negative number? Contradiction, because this sphere's radius wasn't enough to get me back to that xz plane. Okay, let's just look at a few more before we call it quits. Next thing I want to do, we'll just knock these out real quick. Find the equation of a sphere that passes through the origin and whose center is 1, 2, 3. Now remember, I know my equation's x minus h squared plus y minus k squared plus z minus 3 squared is equal to r squared. The center is 1, 2, 3. So I can put a 1 in for h. Oops. I'm going to put a 1 in for h. So it's going to be x minus 1 squared plus y minus 2 squared plus z minus 3 squared, this was supposed to be an L, is equal to r squared. So I've got my center in. How am I going to figure out the r? What I have here is I have a circle that's going, whose center is 1, 2, 3. You draw a little picture. Go over in the x direction 1, go in the y direction 2, go in the z direction 3. So here's your center, 1, 2, 3. And the origin's on that sphere. My sphere might look something like that. How am I going to get this radius? Sure. Distance formula between what and what? Let's find the distance between 0, 0, 0 and 1, 2, 3, right? So if I want to find the distance between 0, 0, 0 and 1, 2, 3, it would be the square root of 1 minus 0 squared, using the distance formula, 2 minus 0 squared, plus 3 minus 0 squared, which gives me square root of 1 plus 4 plus 9, which is square root of 14. Square root of 14. So coming back here, my radius was square root of 14. So my equation is x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals square root of 14 squared, 14. And there's my equation. Okay, just a couple more. What if I wanted to figure out what the center is of this circle and what is its radius? What are you going to do? Complete the square. I'm going to put my x's together. So to bring that 4x over here, I subtract it. I'm going to put my y's together. So I have y squared. I'll add a 2y. I'm going to put my z's together. And I just have 0 on that side, don't I? Piece of cake. Now, I have to make this a perfect square, this a perfect square. Z is already a perfect square. So how do I figure out what this little piece is here? What did we do before? We divided by 2 and squared, didn't we? 4 divided by 2 is 2, squared is 4. So I'll add a 4 on both sides. To make this a perfect square, we take 2 divided by 2 gives me 1. Square it, I need to add a 1, which I better do to this side. Then you're going to factor this. This is x minus 2 quantity squared plus y plus 1 squared plus z squared equals 5. So what is my center? 2, negative 1, 0, right? Because z squared is the same as z minus 0 squared, isn't it? So and what's my radius? Well, r squared's 5, so my radius is square root of 5. Okay, so we did a number of those, so you should be comfortable with that. Okay, just a couple more. All right. Find an equation of a sphere if one of its diameters has endpoints 2, 1, 4 and 4, 3, 10. Now what's happening here is, I'm not going to draw this to scale, but you've got a sphere, and they're giving me one point over here is 2, 1, 4, and another point over here is 4, 3, 10. Now what does a diameter pass through? What does a diameter pass through? The center. Back in your Algebra 2 days. If you had 2 points, x1, y1, and x2, y2, and you wanted to find the midpoint, how did you get the midpoint when you were in 2 dimensions? Remember what you would do? You averaged your x-coordinates and you averaged your y-coordinates. Remember that? To find your midpoint, you would just add your x's together and divide by 2, and you would add your y's together and divide by 2. So in 3-dimensional space, if you have x1, y1, z1, and x2, y2, z2, and you want to find the midpoint, 3D is just 2D kicked up a notch. What are you going to do? You're going to take the average of the x's, that's your x-coordinate, the average of your y's, that's your y-coordinate, and the average of your z's, and that's your z-coordinate. Well, if you have a diameter here, what can you tell me about that point in terms of this line segment connecting those points? It's the midpoint, isn't it? It's the midpoint. So to get its coordinates, I'm going to add 2 and 4 and divide by 2, 1 and 3, the y-coordinates, and divide by 2, and 4 and 10 and divide by 2. So that particular point, the midpoint, is 2 and 4 is 6, divided by 2 is 3. 1 and 3 is 4, divided by 2 is 2. 4 and 10 is 14, divided by 2 is 7. I have the center of the circle, the point 3, 2, 7. And notice, from 2 to 3 is 1, and from 3 to 4 is 1. So in terms of the x-coordinates, it's right smack in the middle. From 1 to 2 is 1, and from 2 to 3 is 1. From 4 to 7 is 3 units, from 7 to 10 is 3 units. So now I have the center. How am I going to get the radius? How am I going to get the radius? The radius is the distance from the center to one point. So what can we do? Distance formula, right? I'm going to use the distance formula. So right now I want to find the distance from 3, 2, 7 to 4, 3, 10. That's my distance from the center to one point. So my radius is going to be square root of 4 minus 3 squared plus 3 minus 2 squared plus 10 minus 7 squared, which is square root of 4 minus 3 is 1, square root gives me 1, 3 minus 2 is 1, square root gives me 1, 10 minus 7 is 3, square root gives me 9, so I have square root of 11. So this particular circle has a center of 3, 2, 7, and a radius of root 11. And just plain plug in, my equation is x minus h squared plus y minus k squared plus z minus l squared equals r squared. So I'm going to have x minus 3 squared plus y minus 2 squared plus z minus 7 squared equals my radius squared is 11. And that will be the equation of my circle. Okay, just one more. Okay, describe in words the region of R3 represented by the inequality y is greater than or equal to 0. Okay, notice when you plot points x, y, z, we're saying look at all the coordinates where the y coordinate is positive. X and z can be anything, but y has to be positive. Well, let's look. If x and z can be anything, y has to be positive. Notice to get your x coordinate, you go over x something. To get your z, you go parallel to the z-axis, up z something. But if y is positive, in which direction do we have to go? We have to go to the right. We have to go to the right. Have to go to the right. Have to go to the right. So do you notice you can think of the x-z axis as being a wall. You see that? It's a wall. And all the points whose y-coordinate is greater than or equal to 0 are all those points to the right of the xz plane. Because every time z is positive, you go over x, go in the x direction, but if y is positive, you got to go in that direction, don't you? You got to go in that direction. So this is the plane to the right, no, it's not the plane, it's half space. It's half a space because this wall, XZ, is dividing space into two parts, and we're talking about the half space that's to the right of the XZ plane. Now for next time, what I would like you to do, for next time, what I would like you to do is read section 13.1, and then you want to do exercises starting on page 833, numbers 1, 5, 11, 13, 15, 21, and 23 to 29. It also would be a good idea to look over section 13.2 before you view this videotape. All right, and then next time we will do sections 13.2. Also, I remind you that if you go onto the Blackboard website that we have, I will have these exercises, the solutions, written out. So after you've done your homework, if you see a particular problem that you would like to see, you can just go to that website. All right, I'll see you next time. Thank you.